This is not the first time that Steve has presented for us, but it's been quite a while. So he's going to talk about a very interesting project that mostly happens in Alaska, but has little tendrils all over the place. So I'll give you to Steve Floyd. Thank you.
Okay, thank you, Eric. Again, I'm Steve Floyd, and I'm the longtime chief engineer, chief designer of the HAARP facility up in Alaska. And I'm still a part-time chief engineer for HAARP up in Alaska. It runs reliably enough, and we have a great maintenance team that I don't really need to be full-time anymore, and that's kind of nice. But what I'd like to do this evening is to have you sit back, relax. I've got about an hour-long presentation, and I'm going to take you through the history of HAARP, why we built it, and the history of why it's in Alaska. We're going to talk about the design challenges, some of the many. We're also going to talk about how we manufactured, installed, and operated the site and how it operates to this day. And I'll give you some examples of some of the science that's done at the site. It's very vast. And you'll come away with a great understanding of what's there, why it was built, and what its potential is and the history behind the project. A couple of footnotes here. Our program office, all through the 90s and 2000s, was here in Washington, D.C. in the Georgetown area. And my home is in the Northern Virginia area. Most of the design activity did take place in our Washington, D.C. office. And we did hire a staff of maintenance techs. They're very well trained. They live up in Alaska. We commuted up to Alaska all the time. And so there's a big connection to the Washington, D.C. area here. And I am a member of the SBE Chapter 37, of course. Okay, before I get started, just a quick little anniversary note here. I was talking to my good friend, Dave Colasar from WTOP just a short while ago. And interesting footnote, I met Dave for the first time up at the HAARP site in Gakona, Alaska. And Dave was working for the Naval Research Lab at that time on one of the diagnostic instruments, or several up at the site. And I was slaving away, and I met Dave up there, and he was interested in broadcast engineering and was just a really bright guy. And he and I have been good friends ever since. So kind of a 20-year anniversary there. Okay, well, sit back and relax. And again, greetings to those that are online as well. Make yourself comfortable. This is going to be about an hour. I'm going to set a pretty good pace here. So if you could hold your questions till the end of the presentation, that would allow me to get through all this information. And then we'll have a question and answer after the presentation. Okay, so the HAARP facility up in Alaska. What is the current status of HAARP? And there's a lot of stories behind this, but I just wanted to bring you right up to the current basic status to get started. The site construction was essentially completed in 2007, which allowed us to go to full power operations at 5 gigawatts ERP at the HF transmitting instrument. That we achieved that in 2007 per the plan. And the site has been improved and expanded since then. But the program and the site, as many of you may know, was shut down in June of 2013 due to politics of money, the good old sequestration budget cuts. Many of you might remember that, where the two political parties couldn't agree on a budget, so they set this doomsday scenario that there'd be 20% across the board cuts for all federal and government agencies if they couldn't come to an agreement on a budget. Well, of course, they could not. And so the Air Force Research Lab, our managing authority, took a 20% cut. And so, of course, R&D projects were virtually all canceled, and HAARP was one of them. So we got shut down in June of 2013. 720 iMac 4CX 10,000D power grid tubes pulled out of sockets, tagged, and carefully packed away. The diesel generators, fluids drained, the site had power cut, it was abandoned and literally just locked up and left to go cold that winter. We were devastated. The project had been on time and under budget the whole time. A 2.5-year backlog of experiments next. But thankfully, in about 9 months later, the site was reopened and restarted when in 2014, when DARPA came to us and said, we got lots of money and we got lots of work to do. So they reopened the site, contractor got a contract, the maintenance tech were still in the area. And I was part-time to help, and we got all the tubes back in, we got all the generators running. And amazingly, the site came up and actually ran very well. I couldn't believe it. So then we got through a year's worth of experiments in 2014. The University of Alaska then, out of Fairbanks Geophysical Institute, who manages the facility now, took over the HAARP program in 2015. And the HAARP program has remained in full operational status with 3 to 5 research campaigns per year since the middle of 2015. So the site is very active and it's very available. And as I mentioned, I'm still a part-time consultant and part-time chief engineer for the site. And sorry, all HAARP conspiracy theories that are out there, and there are many, the human imagination is a wonderful thing. But all of these conspiracy theories, every single one of them is completely false and quite ridiculous. Okay, HAARP. HAARP is a joint program that was built with funding from the US Air Force, the Navy, DARPA, and it is currently operated by the University of Alaska out of Fairbanks. They have the Geophysical Institute there. We were always academically partnered with them. They now run the site and they do a great job. So radio science research in Alaska. Let's go north to Alaska. This picture, by the way, which is a beautiful photo, I did not take this particular picture, our chief scientist did, but this is just a small portion of the 180 tower HAARP HF transmitting array, and that's a sunset off to the west, a very beautiful picture. Okay, why is HAARP important? Well, it's the United States, the USA's only state-of-the-art radio science research facility with premier technical capabilities from ELF through microwave frequencies, including radar and optical light experimentation. The big HF transmitting array is just one of our many instruments at the site, and it's certainly the largest one, and we'll be talking about it a lot. It does have the unique high-power HF transmitting system, which is capable of temporary ionosphere modification for radio science research, cause and effect studies, for example. It does also on site, it's a very large site. It has a comprehensive diagnostic instrumentation on-site suite, which includes, this is not a comprehensive list, but magnetometers, rheometers, radar, imaging devices, many receivers all over the spectrum. We have ionospheric sounders, of course, to get real-time ionospheric measured data to see what it's doing. We have many satellite receivers, general purpose receivers, of course, arbitrary waveform generation, reception capability. We can do all digital modes, pretty much you name it, we can do it. We also have receiving diagnostic instruments that do typically run 24/7. 365 that are collecting valuable long-term observations of the electromagnetic spectrum, very valuable. The facility is located in a region where the auroral oval, and we'll talk more about that, and mid-latitude ionosphere are within our beam pointing view. So this is an optimum location in Alaska for most radio experimentation involving the ionosphere. We get mid-latitude ionosphere, and we can also experiment with this concentrated ring of ionosphere called the auroral oval when it comes down a little bit in latitude. The location in Alaska provides a wealth of research opportunities with very low man-made electromagnetic noise levels and very low probability of causing HF radio interference to any service. Again, we're transmitting vertically within plus or minus 30 degrees of vertical. That's our design space. So the big ionospheric refraction from HAARP is NVIS, near vertical incidence skywave, but obviously it can be heard worldwide. Okay, so this is a rather complicated chart, and I'm not going to take you through the whole thing, but the timeline, I think, is kind of important to sort of get you synchronized with the history of HAARP. In 1990, Congress authorized the funding to go ahead and build HAARP as a premier state-of-the-art radio science research facility with this special capability to work with the ionosphere. In 1993, the design activities were well underway, and in 1994, we actually started manufacturing. We first built 18 towers and 18 transmitters as sort of a test case to prove that we could have a chance of meeting the incredible specs. And in 1995, that's what we call our first light. That's where we actually went on the air with 18 transmitters and 18 towers. Needless to say, we learned a lot. And that really helped us solve some problems we didn't even know we had. Now, in 1999, we had solved all the problems. Our control software had advanced, and all the other ancillary support system designs had really advanced. And in 1999, we had 48 towers and 48 transmitters. And we had that up and running. And I believe that was a total input power of 960 kilowatts at that point. That was input power, not ERP. And everything started working beautifully, and the science was pouring out of this site. So in 2003, we started adding a lot more diagnostic instruments at the site, and we started our final build out for the big transmitting array, 180 transmitters, 180 towers with a 5 gigawatt ERP at HF. And we completed that on schedule in 2007, and we passed all acceptance tests. We did continue to modify and improve the site over the years. We've blown past all the specs and brought new capability to the site over the years. In 2013, we had that unfortunate shutdown due to the sequestration budget cuts. We were shut down hard and cold, and everybody got laid off, much to our dismay. We couldn't believe it. And so we were shut down, power was cut, tubes out of sockets, dark, cold, nobody there, gone. But that only was for 9 months. Then DARPA came back with funding, and we operated for another year. The site performed beautifully. In 2015, the University of Alaska Fairbanks Geophysical Institute took over the site. They got state money, federal money, and we went to a pay-to-play model. And they've been running the site ever since, and they do a great job. Now, in 2017, that's when the University of Alaska really got things going, and we really started a high volume of research campaigns. And then in 2021, we got a big grant, about 8.9 million, I think it was, something like that, or just under 9 million from the National Science Foundation. And HAARP is the centerpiece of what they call the SAGO research program, which is the Sub-Auroral Geophysical Observatory. And it's very vast in its mission. So we obviously work very closely with the National Science Foundation. And in 2022, we started having our open houses again and that sort of thing. So that's a brief timeline. Okay, so here we are, we're going north to Alaska. Where are we in Alaska? Well, you can see the map here. We are north and east of the Anchorage area, and just north and east of the little town of Glen Allen, if any of you know Alaska. And we're in the little town of Gakona. And Gakona, by the way, is an Otna native word. Gak means rabbit, and Ona means river. So we're in Rabbit River, or Gakona, Alaska. Now, why are we there? Well, first, it's U.S. territory. There's essentially a $300 million investment in this site, so we wanted it on U.S. territory. Secondly, we wanted to be at a latitude where within our beam pointing angle, we electronically can steer the beam from the HF transmitter, of course, and many of the receivers. We wanted to be at a latitude where we had access to this auroral oval, which is a concentrated ring of ionosphere caused by the Earth's magnetic field. It's a hollow ring. Many of you are aware of it. And there's a lot of current flowing through it. It's a very opportune experimental spot for the Earth's ionosphere. So it's a good latitude to get access to the auroral oval, but also that mid-latitude ionosphere that I talked about. But most importantly, back in the Cold War, there was an over-the-horizon backscatter radar called the AN-FPS-118. And they had sites built out in Maine, a 3-sector site, huge. They had a site built in Northern California and Southern Oregon, split transmit receive sites, of course, a 3-sector site there. So the Cold War is raging on. And this is back in the 80s, by the way, the late 80s. And so they said, we need a 2-sector site in Alaska to look north for our HF over the horizon backscatter radar, primarily looking for ICBM launches coming out of Russia. So HAARP, that site where we are, was supposed to be the transmitter site, a 2-sector HF transmitting site. They never quite built the transmitting site, but they did one very important thing: the environmental impact statement, $1 million document. So we could come in, well, the Berlin Wall came down, of course, in '91. And they said, oops, you know, we don't need these radars anymore because everything's going to be grand from now on. Right? How did that work out? But anyway, so they shut down, but they put the East Coast and the West Coast FPS 118 sites in a warm storage. They're all demolished now in favor of other more modern OTH backscatter radars that we have. But this site never had any transmitters or towers built, but we had that environmental impact statement. So we could go in and tweak it, and it was perfect for HAARP. So there we are. That's how we ended up there. Now we are in a permafrost area here, which has significant impacts on the construction methods, installation timing. You bore into that in the wintertime, and significant extra costs. We have to anchor our towers and our buildings into a stable permafrost, always frozen crust. There's an active layer above it that can thaw around 5 to 8 feet deep, and the soil moves around like crazy, and then it freezes hard as cement through the winter. So we have to go down much deeper than that, get into this permafrost crust using what's called a thermosiphon that I'll talk about, to get a stable base to mount towers and buildings. So that was a challenge. And as I mentioned, this location provides a wide variety of ionosphere and space conditions that open up a wealth of research opportunities. So here was the site. This picture here is kind of an overhead view of the site. This was taken in the summer of 2003. Thank you, Dave, for the visit. And this was when we were at 48 towers and 48 transmitters. That's kind of in the center of the picture here, which we call the HF high power transmitting array. We have different science pads here, which I'll talk about, that you can see in our operations center. And then in 2007, when we completed the build out, we added one more science pad with more diagnostic radars near the operations center. You can see that's a 42-acre gravel pad. It doesn't look that big in the picture, but that's a 42-acre pad. And that's 180 towers, and that's 30 transmitter shelter buildings, and that is the maximum size of the transmitting array. So a lot of growth took place, but this is effectively the HAARP site. We space things out on science pads, which we'll be talking about. The river that you see on the left, upper left corner there, that's the Copper River. And it's very famous for Copper River red salmon, some of the most tasty salmon if you're a salmon aficionado. Okay, so what's here at HAARP? Well, HAARP is a research and development instrument. We're not really transmitting voice and music, although occasionally we have. But I guess the purpose statement of HAARP is we're using the ionosphere as a nonlinear active medium. The HF transmitter can generate secondary radiation sources at ULF, ELF, BLF, visible light, and IR frequencies. So using this high power HF with a modulation on it, we can create secondary emissions out of the Earth's ionosphere at our modulation rate. And we'll be talking a lot more about that. It can produce radio wave propagation effects. You know, we can alter the radio propagation paths through the ionosphere. We can create different propagation effects to study. And we can create new signal paths, or we can disturb signal paths. We can be very creative there, of course, in our illuminated area. And of course, and so we can affect the Earth's ionosphere and its radio characteristics at HF, VHF, UHF, L band, and all the way up into the microwave ranges in very different ways. So we're all familiar with the radio spectrum here. Key points in this graph are that in the center, you see 2.6 to 10 megahertz. That's the transmitting frequency range of the site. Now, you might be thinking 2.6 to 10 megahertz. Why so limited and why so low in the HF band? The HF band goes 3 to 30 megahertz, right? Well, the reason is we're beaming primarily vertically. Okay, so the maximum usable frequency, or the MUF, when you're beaming vertically into the ionosphere, rarely goes above 10 megahertz. At the peak of the solar cycle, it might get to 11 megahertz. But once you get above that maximum usable frequency, if your frequency, say, goes to 12, 13, 14 megahertz or up, the ionosphere doesn't exist, and you're just transmitting into outer space. So we want to interact with the ionosphere. So there was no need to build the transmitter to go higher than what that vertical incidence MUF would naturally be. Now, obviously, a low takeoff angle that you would have for communications on HF to get an oblique refraction from the ionosphere, there the MUF can easily go up to 30 megahertz, certainly at a solar cycle peak, which we're heading up to now. So that's why we limited it to 2.6 to 10. That's to stay at the vertical incidence MUF or lower. But we can stimulate and experiment with things down all the way to ULF rates below 1 hertz RF. So these very low ULF, ELF rates and VLF rates, lots of stuff going on there. And we're very active up in the VHF range doing satellite stuff and creating mirrors in the sky and that sort of thing. So emerging high power radio technology for next generation DoD systems, spanning 15 orders of magnitude of the electromagnetic spectrum from DC to light. And that is true. We have optics trailers and everything. Okay, let's talk about effective radiated power and capability for a second. HAARP is actually not the only ionospheric heating, that's sort of the slang term, an ionospheric heater. It doesn't actually heat anything temperature-wise in the normal sense. So there's no impact on weather. There's no impact on the problems of the global warming and so on. There's no impact at all. But the slang term is an ionospheric heater. So there have been and are sites that are similar to HAARP, but nowhere near its capability in the world. The vertical axis here is effective radiated power in dBW, or dB above a watt. The blue line at the top is the HAARP ERP capability as it exists now, frequency on the horizontal axis. You see the ERP peaks out at 95 dBW up at the high end of the band, where the antenna aperture is the largest. So we get the most gain, the most narrow beam width. But as we go lower in frequency, because our aperture is fixed, the gain falls off, our ERP falls off, and you can see that in the curve. Then below that is Tromsø, Norway. The Europeans have quite a nice ionospheric experimental site, and you can see their capability there. And then they don't like to do DoD work for some reason. So that's a little bit of a limitation for those folks. And they are still very active, and we do cooperate with them. Now, below that, you see Sura in the Ukraine. I have no idea what the state of that site is. It was built in the Soviet Union days. And we used to go there. I've never been there, but a lot of scientists have been there to do experiments. It's a very basic, rudimentary site. Its ERP and frequency capability are much lower, but they have one feature that we don't have. That's a cool feature. It's a feature I'd like to have, but we don't have it. Only one. And that feature from scientists that have been there to experiment is you open up the back of one of the Sura transmitters, and there's always a bottle of vodka. So after you've done your fix or your tuning, you can get a little swig. Well, I called it repeater, and I'm sorry, not repeater, transmitter fluid. And I tried to get transmitter fluid on our parts list, and it didn't fly. So that's the only feature we don't have. probably a good thing. Now you see some green squares here and it says Arecibo, Puerto Rico. Well, what happened there was they built an HF transmitting site to do ionospheric stimulation and heating that was on the coast. It was right on the coast. And they made their own coax line out of irrigation pipe and had big wire antennas, very large transmitters. But word has it that it had a bad tendency to catch fire every time they operated. So that was a problem, and the salt spray didn't help that. And the big dish at Arecibo was a diagnostic radar to measure the effects of their ionospheric heating. But that's all gone now, and that's been long gone for some time. Then you see High Pass, Alaska on the left here. That is taken down now. UCLA ran a ionospheric heating site up in Fairbanks, Alaska, a very basic site, and it was very effective, but that was taken down and HAARP was built. And then you see the yellow line there, and that was the ERP capability versus frequency of HAARP back in 1998 when we were at 48 towers. Okay, so let's sort of drill down, and we're going to talk about the HF transmitter a lot here, because I know a lot of you folks will be interested in this, and it's very, very unique. And let's start at a HAARP radio tower. Now remember, we have 180 towers, and it's in a 12-row by 15-column grid array, and there's one 20-kilowatt transmitter permanently connected to each tower. And we identify each tower by a row and column intersection. So in the top left corner, we would be column 1, row 1, that transmitter and that tower would be transmitter 0101, and so on. And then the next one down that row would be row 01, but then column 02. So that'd be 0102, and so on. So we have this row column intersection kind of nomenclature for each tower and transmitter, but 180 of these, they're all the same. So what are these towers? Well, the towers are at ground and the radiators are dipoles. And the towers, first, let's go from the bottom up. At the very bottom, each tower is supported by what's called a thermosiphon. Remember I mentioned permafrost. The problem is we need to anchor into a very, very stable layer in our Earth surface that's not going to move on us, right? These are precision aligned towers. So we have to get deep into this frozen permafrost crust. So what we do is in the wintertime, we come in, we precision locate where we want that piling for the tower. We drill down in the frozen soil with a drill, and then we put in a ready-made device called a thermosiphon. That's a 30-foot long hollow pipe that has an arm coming out the side with these two radiator fins, and it's charged with 500 psi of CO2. 500 psi CO2. Charge it once, done. And what it is it's basically like a heat pipe, where what happens in the summer, it doesn't do a thing. But in the wintertime, when it gets more than about -10 or -20 Fahrenheit, those fins on that arm get that cold. And that causes the high pressure CO2 to liquefy at that cold temperature and drip to the bottom of the piling. That's a hollow pipe. And it goes deep into the permafrost layer there, really cold, but down in the permafrost, it's typically +29 Fahrenheit, +30. So then it turns back into a gas. And then it just sort of circulates on its own. So it's sucking the heat out of the ground and super freezing itself passively through the entire winter time, which is 6 months in Alaska. And there is a donut cap of blue board that's about, I don't know, 4 feet thick, 10 feet in diameter, that's under the gravel on top of it, so we get a little R value. But in the wintertime, we're super freezing into that stable permafrost crust 30 feet down. And then in the summertime, it just doesn't do anything. So we can get through the summer, very stable. As we come up this support tower, you see the ground screen. This is an 18-inch square open AlumaWeld ground screen that is our ground plane. It's a flat metal plate as far as RF at 2.6 to 10 megahertz would see it. So we establish a flat ground plane, and the shelter buildings, walking around, driving, we're all under the ground screen, gives us a beautiful ground plane to reflect energy off and back up. We come up the tower, we get to a high band set of dipoles. Now we actually have crossed dipoles, a north-south dipole and an east-west dipole. and they're independently fed by the same transmitter. That way we can do any polarization that we want. We can do circular left, circular right, all by phase, which we have absolute control of, and we can do elliptical or linear. But we're just looking at one plane here, but keep in mind, these are cross dipoles. So we have a high band set of dipoles. They cover, I believe, 7 to 10 megahertz. And there are 3 wires in parallel, shorted at the ends. And let's call this the north-south, and there'd be an east-west coming in and out. And we have the high band antenna matching unit that has our Balun function and impedance matching and vacuum relays in it. We'll talk more about that. So we're trying to be a quarter wave off that ground plane at 7 to 10 megahertz, because as many of you know, when you're a quarter wave off the ground plane, you reflect energy off that ground plane and it goes back up. It reinforces your pattern up. And if you were half wave above that ground screen, you would have a null going up and you'd be reinforcing out the side, which we don't want. So we're trying to stay a quarter wave off the ground screen. So then when we go to our low band, obviously the wavelength gets longer, the dipole has to get longer correspondingly, and we have to move up higher off the ground screen to get to a quarter wave. And this is a 3-dimensional fat bow tie wire cage with metal arms at the top. And then we have a low band antenna matching unit, again, crossed dipoles, and that's 2.6 to 8.4 megahertz. So that's what a HAARP tower looks like sitting on its thermosiphon. So here's a picture. And once again, this is a 12-row by 15-column array. And there's 1 transmitter married per tower. And you're not seeing the full array here, but what's good about this picture is, one, you can see the thermosiphon here. See that white piling on the right side here? And you come up and there's 2 radiator arms. And that's where that cooling happens of the high pressure CO2 in the wintertime to, condense the CO2 and then drop it. It just drips down, of course, as I said, and then it comes back up as a gas. So that's the radiator arm for the thermosiphon there. Then you come up the tower and you can kind of see, if you look up near the top, you can see this grid kind of ground screen here, and it's all crimped and everything. It's very nice. And then you can see the big arms in the towers here. That's the top of the 3-dimensional cage dipole for the low band with its matching units. And then below that, you see these other round cans, and those are high band matching units. Now, these white trailers here, they're not actually trailers, they're custom built. They're only in this shape to get it on a flatbed to bring it out to the site. They're custom made shelter buildings that have 6 transmitters inside. Everything is operated over a local area network. Nobody has to come out there at any time to operate the site unless you want to do some maintenance. So it's all operated environmentally and all transmitting operations over a local area network. Okay, let's zero in on a tower here. So if you look at a tower here, this is very interesting. If you look near the very bottom of this picture here, you see 2 little square boxes. Well, that's what I call the high band, low band switch. So we have 2 feeds. We have 2 feeds coming up each tower. This is 1 5/8 coax. We bought it from RFS. It's solid foam. There's no air pressure inside. It's 1 5/8 inch coax with 1 5/8 EIA flange connectors. And so each tower has an east-west dipole and a north-south. So we have 2 outputs from each transmitter. One is the east-west output, one's the north-south output. But I have to switch it between high band and low band. So those are the switch boxes. If we come up farther up the tower, you see a north-south and an east-west antenna matching unit, the round cans. And then you see these little boxes here, and I'll talk about that in a second. Then you go higher up on the tower, you see the low band dipole booms, and there's a 3-dimensional wire cage that is supported. That's to reduce the Q and give us more bandwidth. And then again, you see the 2, you can kind of see there's an east-west and a north-south round can antenna matching unit. And again, you see these square boxes. Well, what are these square boxes? Well, these square boxes are called even mode loads. They're dump loads. You're thinking, wait a minute, what are you putting dump loads on a tower for? That's not good for ERP. But we learned when we built the first 18 towers, we learned a big lesson. When we got all the transmitters working beautifully, and I was very proud of that. But every night we came up and ran, we would burn up one of our early matching units. We were burning them up like popcorn. And at first I thought, hey, I'm the transmitter guy, you know, and what does a transmitter guy want to do? We want to burn up stuff on the tower and say, look, my transmitter's good. And they're like, wait a minute, I got to fix the tower too. So this is not good. So what we eventually figured out was that we had not accounted for something that was extremely important in an array of this size. As you'll see in coming pictures, the dipoles are actually very close to one another, especially the low band dipoles, the longest ones, because the government did not want to have two arrays, too expensive, too much coax. They want one array of 180 towers. So we stacked the high band dipoles lower on the tower underneath the low band dipoles. And then when we want to use high band, we have vacuum relays where we float each half of all the dipoles through a static drain choke, and they disappear because they're not resonant. And then vice versa, when we go to low band, we open vacuum relays and float the half dipoles in the high band, they vanish, and then we transmit on the low band. Now we do trade off some gain in the low band because we're not optimally spaced, but we have one array, and that's great, except for one problem. The low band array, the dipoles are so close that by physical proximity, we get an effect called mutual coupling, where if I'm at one of the transmitters or looking at it in the ops center, and I see, oh, my SWR is 1.7, and then in the neighboring transmitter, we turn that off, then the SWR goes to maybe 1.4. And so a lot of the reflected power coming back is not from your own dipole. It's from other transmitters 2, 3, 4, 5 columns away that are coupling over to you dependent upon frequency and phase just by simple proximity. And what we discovered was we had hotspots that would move around in the array as a function of frequency and phase of this even mode power that was peaking very high, and its mutual coupling by proximity. And now I'm saying even mode, and that's the key here, because if you're going to transmit power, it's in the odd mode, meaning you have a current distribution over the dipole, but you always have opposite polarities at any moment in time on either side. So it's like plus minus or minus plus. That's odd mode, and that's what can radiate and receive. Although this is just a transmitting site. But what if you have even mode power from mutual coupling effects where it's plus plus on either side or minus minus, the same polarity on both sides? That's real power, but it can't radiate. It physically cannot. So it has to find a return through the matching unit and back through your grounds to get back to the source. And it was creating, peaks of even mode power up to 10 kilowatts. And these hotspots would move around by frequency and phase, and it was causing our matching units to burn up. So we redesigned these matching units, which I'll show in a minute. And if there's even mode power there, it gets thrown into a convection cooled dump load. And Kentronic Labs built these for us and did a great job. But if there's no even mode power there, they just don't get any power. So it's to take care of these big hotspots that move around the array so we don't burn up our matching units, and we don't have a lot of RF current coming down the tower and in the shack where we don't want it. So those are even mode dump loads. They work beautiful, stabilize the array. So here you're seeing those two sets of nested cross dipoles. You see low band 2.6, 8.4, high band 7 to 10, unique fat bow tie geometry. Everything is completely welded on the dipoles and the ground screen, and everything is designed to survive 100 miles per hour with lots of ice. Okay, here's an antenna matching unit. Let's talk about that for a second. One of the requirements we had was to have this even mode dump port, which you see actually on the very bottom, just a little bit up from the very bottom in the center there. That's a 716 DIN connector, and that's my even mode dump port. And if even mode energy is there, we throw it off as heat. If it's not there, it doesn't do anything. But what you're seeing here is this is double shielded, silver plated, tape wound dielectric Teflon center coax that was specially made by Times Wire for us. And this is a 4-port TEM mode hybrid transformer. And we have some lumped L. There's a vacuum cap there, and then you see the vacuum relays. You see that up on the left there when we have to float the dipole where we're not using it or want to use the other band. So what this 4-port hybrid transformer does is it has the Ballon function, very important. It has broadband impedance matching, very important. But it also has that even mode port that if even mode power is there from the mutual coupling effects, it goes out the dump load port and stabilizes the array. And notice what's not here. You notice something missing? Where's the ferrite? There is none. We were not allowed to build any transformers with ferrite because when ferrites saturate, you can generate a harmonic content. Oh, they don't want that from HAARP. Even low-level harmonics at 5 gigawatts are a problem. So this had to be a no ferrite design. Everything is bolted or welded. And the insertion loss, worst case, is 0.2 dB. Amazing. And it's charged with dry air once, and a lot of them are probably flat now, but that's okay. Okay, let's talk about transmitters. In the HAARP shelter buildings, which you see in the lower left here, it's a custom-made building by ABC Trailer. We have a control rack on the left with all of our phase control and our networking and so on. We have 3 transmitters on the left and 3 transmitters on the right. The capability, of course, as I said, is 2.6 to 10 megahertz continuously. We never operate in the ham band. We're not licensed to. We do have an FCC license, but we're not licensed to in the ham band, and that's locked out in software. Each transmitter has dual independent outputs. We'll talk about that more, but 10 kilowatts on the east-west side, independently tuned, 10 kilowatts on another amplifier on the right side, independently tuned. So for each 10 kilowatt amplifier, we use 2 iMac 4CX 10,000D power grid tubes in grounded grid, cathode-driven push-pull for a 10 kilowatt amp. And there's one of those on the left side, one on the right side. Why did we do that? Well, we're designing this in 1993, 95. LD MOS, which is so rugged now, had certainly not come along. It was too expensive to attempt MOSFETs. Power grid tubes, they're still available, and they're rugged. They like to get hot. They can take abuse, and that's helpful to us. So it was also cheaper, and the plate tank, the tuned plate tank, actually acts as a bandpass filter, helping us to meet our extreme harmonic and spurious requirements. So it was the right technology for us, and we get very long lifetime. But that means there's 4 tubes per transmitter, right? We got a push-pull pair on the east-west side of the transmitter, and we got a push-pull pair on the right side, the north-south side. That's 4 tubes per transmitter. And then, oops, wait a minute, I've got 180 transmitters. That, my friends, is 720 iMac 4CX 10,000Ds active in sockets, and that is correct. So I went out to iMac when they were back in San Carlos several times, and let me tell you, that's the only time in my life ever that I've had a red carpet rolled out. And I took advantage of it. So anyway, it's all iMac. Now, one other note here is, why do we use 2 4CX 10,000Ds for a 10 kilowatt side? Well, obviously, the 10,000 is the plate dissipation rating, not output power. But the main reason for 2 tubes in push-pull was to reduce the second harmonic. A push-pull pair, as many of you know, naturally rejects the second harmonic, and we struggled with that, and they were willing to pay, so we put 2 tubes in push-pull, and I thought, boy, I want 20 kilowatt a plate cooler, because I knew I'd be facing bad SWRs at times. So anyway, that's the reason. So we have an automatic antenna tuner built in, graceful degradation for VSWRs higher than 5 to 1 that we can tune to. Look at the bandwidth available, 200 kilohertz. That's big for HF, right? I mean, a single sideband signal is what, 3 kilohertz? A broadcast station might be at most 20 kilohertz. And we have 200 kilohertz, but that's at the low end of the band. At the high end of the band, because of the plate tank Q, that rises to 500 kilohertz of bandwidth I have to play with. Oftentimes, that's larger than the whole band allocation we have, so we stay within it. Look at the harmonic and spurious here. In band, up to 10 megahertz. Harmonics and spurs are greater than 80 dB down, standard broadcast spec. But out of band, minus 120. And up in the VHF band, where broadcast and wildlife tracking folks are, they were panicked about us. We're 150 dB down. That's an incredible spec and it's real. We did meet that. We can do CW, AM, FM, and pulse with user-defined rise and fall times to control our occupied bandwidth. And we can do all those modes simultaneously. We can be doing AM and FM simultaneously and be pulsing. We can do all these simultaneously. It's really an arbitrary waveform generator. And there are 6 transmitters in a shelter building. You can see in the bottom left a shelter building here, and you see coaxes coming out to towers on the right side and on the left side. We're going to come back to the transmitters here in a minute to take a little deep dive. But here's the control center for HAARP. We have a building up there that's the control center. It has a kitchen, it has many offices, many labs, spare parts areas, and so on, a ham shack. Our ham radio club call sign up there is kilowatt Lima 7 effective radiated power. And if you ever hear that call on the air, somebody is actually at the site. And I do activate it when I go up there. Now, somebody I was talking to earlier had a great observation. He said, why didn't you just have fun and call it KL7QRP? I'd never get away with it. This is the ops center here, not the ham station, unfortunately. And so the operator sits in the center here. It's all run by GUI software. It was written in C++ and it runs under Linux. So everything is pre-run and scripted, so we can automatically step through experiments. I'll talk about that more later. On the left side, we have environmental control. We have aircraft alert radars on the left. On the right, we have all kinds of monitoring instruments. We have full remote control of our power plant, which is huge, which I'll talk about in a minute. On the far right here, those are 2 Motorola aircraft radios. The FAA was very happy with us for many reasons, but they said, you know, we need to have a base station there so a plane can contact you if they're worried about flying over when you're transmitting, which we have ways to not transmit when planes are in the area. But we said, fine, so we have our own calling channel there in the aircraft band. Okay, how in the world do we keep track of 180 transmitters? How in the world would you do that? So we agonized over this for a long time, and we came up with this approach here, and it's the coolest thing you've ever seen. What you're looking at here is if you were a bird and you were over top of the site, looking down, and let's go to the top left corner. See that A there? That is what we call shelter column A, and there's those 6 transmitters that are in the geometrically correct position, and also with the towers. You walk into the right side here of that cluster of 3 where it says A, and that's shelter A1. Go down to the next 6 grouping there, shelter A2, and if you go to the right, B1, B2. So we have the same row column for the shelter buildings, but those transmitters are all geometrically correct for position. The shelter buildings are geometrically right, and they're geometrically matching the towers as well. So what you're seeing here is green is forward power and blue is reflected power. So up and down is north-south and left and right is east-west. So let's go back to that top left corner. My forward power is green and I want reflected power, which sits on top of it as a blue bar. And then left and right in that first little box in the upper left would be I see it's north, south, up and down, and east, west, left, left, and right. So we thought, why have these 2 little bars with nothing in the middle? So we just make them form a box. The software just draws a box between the maximum reflected and the maximum, and it's a box. And that way, if one of them drops off the air, it collapses to a line. So you can see the SWR is better in the center of the array, but this is 180 transmitters. Now, this is a rare shot in the sense that the 3 transmitters are off the air and they have an A in the middle. Those obviously are not transmitting, and their antenna matching unit relays are open to the half dipoles, so we're not shoving RF back in them from the neighbors, which would happen if we left the antenna bands open up in the matching units, those relays. But those 3 are offline. That almost never happens. We almost never have a transmitter down. But I grabbed this picture early on just to document what it looks like. And A means antenna band open, meaning those vacuum relays and those antenna matching units are open. So we don't get power shoved back down into an off transmitter. And obviously they're not making any power, but keep this picture in mind here. There's other data I won't go through, but this is 180 transmitters, 360 10 kilowatt amplifiers, right? 2 per transmitter. So now, this is just an example. We meter everything in these transmitters: plate voltage, plate current, stack temp, driver power, driver SWR, forward reflect, input temp, 480 volt 3-phase current. That's our prime power, 480 volts AC 3-phase for prime. We meter everything. So what the maintenance techs can do is they can pick any meter reading they want to look at array-wide and assign a color temperature scale to it. And then they can see outliers to see who needs maintenance. So look what's happening here. In this red box in the top left, PA1, that's my east-west left side of the transmitter forward powers. And you can see a few are orange, meaning they're a little bit low in forward power. You can see the 3 that are off. And then directly below it, you can see those same transmitters with reflected power. That's there. So the top left corner of this blue guy, and the top left corner of the orange guy, those are match forward and reflected power. So you can see the outliers here, and maybe vector you to what needs to be worked on. This can be done for anything: stack temps, line current, driver powers, whatever you want. And so then you go to the PA2 column here on the right side. That's the north-south amplifiers for all 180 transmitters. Same concept. You can see a few orange boxes here, a little bit low in forward power, and you can see the reflected power. And oh, look what we have here. In the PA2 column, in the bottom left corner, oh, there's a green. That's a lot warmer. That's a lot higher. And ooh, his reflected power is 4.6 kilowatts, it looks like. But his forward power up in the top one, the bottom left corner, is 10.3. So it's like, uh-oh, that's high reflected power. It's an outlier. We need to go work on that tower. So the maintenance techs, they love it and they hate it. They get bored when we're operating, but they scroll through all these different parameters, every little thing, and they look for outliers by color temperature that stand out, and they know what to work on tomorrow to keep everything just right. Okay, one of the other unique things about the HAARP site is we have current monitors attached to every balanced output of every antenna matching unit for both the high band and the low band. We bring those samples back. And so what we're sampling is actual dipole RF current that's actually on the dipole. And we can see frequency, we can see magnitude of current, and we can see phase. And so those come into the shelter buildings on 3/8-inch heliax lines. We do an A to D, we bring that all back over the LAN, and then we use a NEC4 model of the site. And we quickly calculate the pattern in a 3-dimensional display. So we can see our radiation pattern in real time. How about that? And we can see it moving around and get it fat, and we can see what the side lobes are, and we get data. So this says from actual real-time data from current monitors in the whole array and our model, it says in this case 3.4 megahertz. We're off the main vertical axis by 14 degrees in one plane, and we're off another one minus 158. The gain of the array, you can tell an engineer did this. Oops. 22.658 dB. Engineers. What are you going to do? 3 decimal places per gain? But that's what I did. And so anyway, we can see gain, we can see ERP, 6.378 megawatts and so on. But look at this. We have the capability to arbitrarily operate on 2 different frequencies at the same time. The user, the scientist, can pick any pattern he wants. And you say, I want these transmitters of your 180 in this pattern. It can be every other, it can be a block here, but anything. You say, I want these transmitters with the pattern they'll make to be operating on frequency 1 in some mode. It might be FM and pulsed. And then he says, I want the balance of all the rest of the transmitters at frequency 2. And I want that to be a full power carrier with a phase mod on it. Just a solid carrier. Okay, fine. No problem. So we have this dual frequency capability. You can arbitrarily assign any transmitter to and let them operate simultaneously. Very interesting science. So in this case, the higher ERP is measured and modeled in the red here. So that would be the left column here up top, 6.8 megahertz. You can see the pointing angles. Power is 4.702 megawatts. ERP, you can see the gain, and then the other is 4.5 megahertz. lower ERP 2.573 megawatts ERP, and the gain of whatever the pattern was there. So we can see both these beams moving around. We can see the side lobes and everything else. One interesting comment, scientists are so creative and we love it. And so, they'll say, well, I want a really low takeoff angle. We're like, well, it's designed for plus or minus 30 degrees of vertical. I was like, yeah, but I want the lowest angle you can give me. I want to do some over the horizon backscatter radar, which we do all the time. And we're like, fine. So we push the beam down, and all of a sudden the back lobe on our model comes up. And sometimes our back lobe is bigger in amplitude than the forward lobe, because he's so far out of the design space. And SWRs get crazy in the array, but that's what they want. So we do it. So it's a really handy tool. Okay, how do we power all this? Well, we have our own power plant. Now, we do get three-phase AC power out of Valdez. It's hydroelectric power from a glacier lake and leftover pipe, 4-foot diameter pipe. 2 pipes come down to two hydroelectric generators. But Valdez is 160 miles away over 2 mountain ranges. And it's 3-phase power. We're supposed to get, I don't know, I think we're supposed to get like 900 kilowatts. We can barely get like 300 kilowatts, and the phases are all over the place, and the voltage is all over the place. And we have to call them on the phone and tell them when we're going to come on, because they have to manually get more water going. It's a real mess. But we do run our offices on the Valdez power. But for the transmitters, there's no way they could handle our load, and they couldn't handle the pulse. So we have our own power plant here. There are 5 of these EMD diesels, compressed air start. Radiators are outside. And each one is rated at 3,600 horsepower. The total power generation capability of our 5 EMD diesel power plant. These are former locomotive diesels, by the way, that had turbochargers added, and they auto sync through the electronics from the pulse rated generators. But the total capability is 16.25 megavolt amp, about 13 megawatts with a power factor of 0.8. To operate the entire transmitter array, that's what we use the generators for, to run the transmitters. And we generally stay on outside power for offices and diagnostic trailers elsewhere on the site. But we can island completely if we want to, and we have quite often. So to operate the full array, we need only 4 generators. We got a spare. That's 10.4 megawatts of capability, and we don't quite need that much. We'll talk about efficiency of the transmitters in a minute. But here's a key point. And no broadcaster would ever, in their right mind, would ever sign up for this. But if all transmitters are properly tuned, putting out full 20 kilowatt total with a CW 100% duty cycle, with that power draw, which is on the order of about 8.5 to 9 megawatts, with all the blowers and everything added, we're consuming 500 gallons of Arctic grade diesel per hour. 500 gallons an hour. And it was like, even back then, it's over $3 a gallon. So that's kind of expensive, but that's what we have to do. We have 3 above ground diesel tanks with Arctic grade diesel that doesn't gel. It's more like a JP4. It's what they refined to up there. So we have 1.2 MVA of commercial power. It's really only about 600 kilowatts coming out of Valdez. Okay, let's talk about a few of the other systems. Then we're going to come back to the transmitters, a little science, and then we'll wrap this up. So we have the FAA came to us and said, can you guarantee that you'll never be a hazard to flight with this big ERP? Well, you can't guarantee anything 100%, right? So what I did was I took a 60 kilowatt Bruno maritime radar S-band and put it on a special platform where I tilted it up where the half power beam width is at the horizon, and we spin that around. We took away the shipboard terminal, did our own software PC terminal with tracking and everything, and we can track planes with that. Then on the shorter tower with the dish, we have a TCAS. If any of you are pilots, this is the collision avoidance system. That's an automatic Mode S transponder interrogator to avoid collisions. Well, we took one of those high power mounted it on a flat plate. It's just like an antenna you put on a plane. And we can walk it up and down because it's only looking plus or minus 10,000 feet, but we can walk it up and down and it's pinging aircraft transponders that are within range, but they don't see us. We're just a pinger. We're not a responder. So we have tracks from their transponders. And then lastly, we have ADSB at another shelter building. So we get 3 inputs and we have 3 radar displays. And if an aircraft comes within 5 miles of the site, the software automatically stops transmitting until the target gets out of 5-mile radius or it coasts if we lose a track. And the FAA loved it. So we're not transmitting when aircraft are overhead. It's a technical solution to a political problem. Now let's talk about the transmitters a little bit here. So the transmitters, 50% were designed here in Washington, D.C. in our office. We designed everything for the software, the networking, the control, the drivers, everything except for the power amplifier and the high voltage power supply in the cabinet. That was done by Continental in Dallas. But we paid Continental to assemble everything and test for us. So here we're moving a Continental transmitter. We left the Continental nameplate on it, but it's 50% built by us. Going into a shelter building, we install them all. Here's a transmitter that's been QA'd and ready to go back against the wall. That's a 3-phase transformer, 480 is our prime power. That's a 480 input. And it has the high voltage outputs for the tube and the screen voltage and so on. You can see the 2 1 5/8 CIA flanges. One is an antenna output. One is for a dummy load for testing cow. A little closer, you can see a tuning coil here. It looks rectangular. It has sliding contacts, but that's a tuning coil by a stepper motor, and that's for the adjacent transmitter's antenna tuner. So here's a side view. You can see the antenna tuner coil here on the right. You can see the 2 outputs. This is the plate tuning coil here. There are 2 4CX 10,000Ds. There are tuning caps for the plate tuning and a big cap for the antenna tuner. Now here we are after QA pushing the transmitters in. We're putting them up against the wall. We can do all maintenance from the side. We come in at the bottom at plus 10 dBm. We come out about 20, 30 watts. We have a broadband 1 kW solid state amp, MOSFETs, nominally about 500 watts, driving the push-pull pair, and then hot air comes out. So the left side is east-west, the right side is north-south, high voltage power supply in the middle, and metering and breakers. So 3 transmitters on the left, 3 on the right. Now, one thing to point out here, you can't really see it that well, but the floor is a supply plenum. We have 1 ginormous blower at the end of the shelter building, sucking air from the outside through filter media, charges the floor. And then we have holes that blow the air up through the transmitter from that single blower for all 6 dual transmitters. And then the hot air comes out at the top. It's 1,500 linear feet per minute. It's a lot of air. Okay, here I am calibrating transmitters. One unique thing, you can see the 2 stacks here, but we calibrate each transmitter like a piece of test equipment. We went every 500 kilohertz through the band and precisely tuned each transmitter for linearity, gain, and amplitude flatness, because I'm sweeping it with a network analyzer. I turn the AEGC off, and I can sweep the entire transmitter while it's into a dummy load. I have directional couplers in the output, and I can sweep it with a network analyzer. Continental had never seen that done. They thought I was crazy, and then they thought it was the greatest thing they ever saw. So we calibrate each 10 kilowatt amplifier for tuning every 500 kilohertz. And we're adjusting stepper motor offsets, because we have stepper motors for the coils and stepper motors for the vacuum caps. So I end up with a cal file for stepper motor offsets for tuning for each amp, which we save in the computer for the transmitter. And then I do a power cal every 500 kilohertz. And I calibrate into special watt meters into the dummy load. But then what do I do for frequencies in between? I do what's called a spline fit in software and interpolate the cals in between. Works perfectly. They're almost as good as a piece of HP test equipment, the way these things are calibrated. So we calibrate each one. Okay, so here's a finished HAARP transmitter building. You see the 3 transmitters on the right, 3 on the left. Those are QA sheets. They really are this clean. Again, under this mat on the floor is that supply plenum. The blower's way back in the left, and then the return plenum for the hot air is in the ceiling. That's a common return plane. And our environmental control system automatically mixes the outside air, which is generally cold, not always, but we mix it with our exhaust air to maintain a constant 55 Fahrenheit supply temp. So we reuse a lot of our own heat, obviously. Okay, here's an aerial view of the HAARP site. That's 42 acres there of the transmit array. You can see our op center building on the left. That's Mount Sanford in the background, about 25 miles away. We're way too far from Denali, way too far away. But this is in the Wrangell St. Elias. You can see our ionospheric sounder in the lower center, and then we have a satellite pad here. And so that's just an overhead view. This is a picture of the HAARP array. I was going in one morning, and this was a sunrise, and there was a little bit of frost on the ground screen and all the Philly strand that pulls everything tight. And that's a beautiful picture there, a lot going on. And let's talk about the auroral oval and a little bit of science here. Here's a picture in the upper left, kind of showing the auroral oval and the effects of the energy from the sun. There are satellites that image the auroral oval. It's a concentrated ring of ionosphere that is hollow in the middle. It's formed by the Earth's magnetic field, and it gets bigger and smaller and sometimes breaks into multiple ovals. Again, we want a power beam into that auroral oval to try and modulate the electrical current flowing in it for science. But that's the auroral oval we're interested in. And here's a manifestation of the auroral oval. This is our optics trailer on one of our science pads with high sensitivity CCD cameras. But this picture, a little bit of time exposure here, but this is a picture of the Aurora. And that Aurora, that curtain of Aurora, is painting out the auroral oval. When you see these curtains of Aurora, going across the sky, that's either a fragmented or the actual auroral oval of that concentrated ionospheric ring that sits about the North and South Pole. So that's a beautiful picture. Okay, so let's talk a little bit about the science here. One of the things that HAARP does, it does everything from communications to over-the-horizon backscatter radar to ionospheric stimulated emissions. It just goes on and on. It's a sandbox. It's a scientific sandbox for radio experimenters to play with. Again, nothing to do with weather, nothing nefarious. And we operate on a no interference basis, and it just fills up the physics journals. So this is an example here where HAARP might be transmitting on an HF, it would be transmitting on an HF frequency, and the absorption is the greatest in one of the circular polarizations. I can't remember which one. And if you're at a frequency that's just below the actual measured MUF at that moment in time for that hour. So we look at our ionoson, we see it, say if the MUF is 5 megahertz, so the ionosphere vanishes if you're above 5. So we might operate at 4.8 if that's the part of the band we're allowed to. That's where the absorption is going to be the best. And the experiment will have waveforms on our transmitters. It could be anything, it could be multiple frequencies. But in this example, we have the natural currents that flow in the auroral and equatorial ionosphere at about 80 to 100 kilometers up. The HF signal interacts with the plasma conductivity. They're saying at roughly 80 kilometers on this slide. The electric jet current is then caused to vary at our modulation rate. And so a simple way to explain it is if I came up, let's say at 4.8 megahertz, and I put a 100 hertz square wave, that's my AM source, all done through DSP software. So my effective radiated power is going up and down, at 100 hertz, just 100 hertz AM, a tone, if you tuned it in on the radio. Well, that simple AM would interact with the free electrons up in the ionosphere, and it would stimulate out useful, coherent RF at our modulation rate. And that's a powerful thing, because think about 100 hertz. Anybody know off the top of your head what the wavelength is at 100 hertz? Well, I can tell you it's what?
3,000 kilometers.
It's 1,864 miles. So that's probably pretty close. So a wavelength is 1,864 miles at 100 hertz. And you say, oh, well, I only need a half wavelength for a dipole. Oops, that's 932 miles. So how are you going to build an antenna with bandwidth and then get it high enough above the ground to get a useful radiation pattern? Not going to do it. Plus the politics would get in the way and everybody's cows would stop producing milk, of course, and it would be a big mess. So this is a way where we can stimulate ULF, ELF, VLF radiation at our modulation rate. They can do all kinds of different waveforms. In fact, they electronically scan the beam back and forth and excite a region of ionosphere oftentimes that's a half wavelength long to get more efficiency. And it works great. Now, it's not a lot of power. It's not that strong, but it's strong enough. And you can use lossy receivers to do ground penetrating radar work and ocean penetrating radar work and so on. So that's a big area of exploration. Here's an example. We have a receiver in Chistachina, Alaska, about 45 miles away, with these lossy negative gain, 10-foot long, ferrite loaded coil antennas, but they work, and receivers. And I don't know if you can see this, the bottom picture is better, but audio frequency modulation, in this case RF frequencies on the vertical axis and time is on the horizontal axis, kind of like a sideways waterfall. But they got a program where we were transmitting multiple tones, and look what they sent, HAARP, HAARP, that was transmitted in stimulated RF at audio rates and received. And this was done before we had all of our transmitters up and running. So it actually works very, very well. Just a way to show off how we can generate this low frequency RF. So why do we want this low frequency RF in this experimentation example? Well, the skin depth of soil and water can be many kilometers deep at these low RF frequency rates. So there's a mining school up in Delta Junction, Alaska. All they do is move rock, but they train them how to mine. So that's a target of opportunity. It's about 100 miles north. So we can characterize that environment. And in this case, ELF, VLF waves penetrate ground and can detect and image underground targets. So you see the heater, that would be HAARP, transmitting RF, and you get ULF, ELF, or VLF, depending upon our modulation rate, and we can modulate up to 30 kilohertz in AM. And we can stimulate that RF, and it comes out in a pulsed format. And then we can actually, in a radar ground penetrating mode, image what's underground. And this actually works rather well. And so the military is interested, right? Because they could put receivers on RPVs or airplanes or whatever, and HAARP may or may not be the source. But if you get the pulsed RF and you have proper signal processing behind it, the potential is you can overfly a bad guy's area, and you can image in 3 dimensions, caves, tunnels, bunkers, complexes. You can also image natural resources, oil deposits, which we're not so interested in now, but other natural resource deposits and so on. And then in the oceans, you can communicate to deeply submerged subs with much higher data rates. You can image the ocean floor. You can find subs that are sitting and not moving, for example. Okay, here's an example where we actually hand walked a receiver over this mine, and you can see with rudimentary signal processing, there's the image that we got that was with low frequency RF stimulated out of the ionosphere from HAARP, and how we're imaging the tunnel at that depth. But this was again done with only 48 transmitters, and the software is far beyond. So that's an example of science there. Now here's an optical example here. If we just pointed HAARP up into the night sky, a moonless sky, no modulation on the carrier, just a carrier. And it's just interacting and exciting the free electrons in the ionosphere with a high sensitivity CCD camera. That's the artificial Aurora that HAARP is creating with our 5 gigawatt ERP or slightly less. Now, I've never seen this with my bare eyes. Some people claim they have after how many beers, I don't know, but I've never seen this with my bare eye, but with a high sensitivity CCD camera, you can clearly see this. But again, there's all kinds of optics experimentation going on. Okay, here's another example of science here. We can create what are called wave ducts. We can also create disturbances in the ionosphere to cause what's called scintillation of satellite signals. The GPS guys love this. We can create ionospheric distortion effects for satellite signals, especially GPS, on demand and of different types. So they can try their software algorithms that are trying to get rid of it, when it occurs naturally, but they can't wait for years to try and catch it we can make it for them. So that's a nice use. We can also create field-aligned irregularities, just like transmitting a high-power carrier, and VHF, the ham 2-meter band. We can create mirrors in the sky, and it's very efficient, and you can all of a sudden reflect off of that and get propagation for thousands of miles. We stop transmitting, it goes away. We transmit, it comes right back. So we can create VHF mirrors in the sky, and that's a good example. So I just wanted to comment briefly here, and then we'll wrap it up. We're located in Gakona, Alaska. Now, Alaska is a very unique state. If you've never been, you must go. Go in the month of August, don't take a cruise, go online, stay in the lodges and the B&Bs and drive, and it is a great experience. But we're in the little town of Gakona here. And of course, projects have their ups and downs, and ours certainly did as well. And there's a bar in the little town of Gakona, they all know as well, and it's called the Trapper's Den. And here's the welcome to Gakona, and there's the bar right there. Every Alaska town has many bars. And so there's the Trapper's Den bar. We had many meetings, many nights, cried many tears, and that was our hangout place. We also got good food there, and it's just a great experience. Now, let me warn you about something in Alaska, and you'll thank me for this. Any bar in Alaska, Anchorage, Fairbanks, Gakona, anywhere, you'll see something in these bars that you do not see here. And what you'll see is hanging over the center of the bar, where you can easily see it, is a bell with a little pull cord on it. And you'll see one in every single bar, the schwanky places and the dives. They all have a bell above the bar. And the thing about the bell is, if somebody, and this is from the old gold rush days, if you come in there and you've struck gold and you've got a lot of money in your pocket and you want to celebrate, and if you walk over and you grab that cord and you go ding, 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 and ring that bell, you just bought everybody in the bar a drink of whatever they're drinking. And I've been sitting in bars in Alaska, all over the state. I was saying ding, 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 we're like, okay, I don't know who rang it. So be careful. They also, you also take a dollar bill and staple it on the ceiling and sign it. That's another big thing in Alaska. Okay, one of the things in Alaska that's really fun here is, remember I said we're on the Copper River. Well, the Copper River is known for salmon. Many of the rivers, of course, have salmon. And this is called a fish wheel. And this is a very ingenious thing. The natives in Alaska obviously subsist on salmon. And it turns out that salmon, when they spawn and they come up the river, they don't come up the middle. Who knew? They come up the sides. I guess it's better swimming, but they come up the sides of the river, always. So they created, and these are all home built. You have to license them. Tourists are not supposed to use them. It's for subsistence. All towns have them. And it's an automatic salmon catcher called a fish wheel. And it's the simplest but most effective thing. Notice the cable on the left. It's anchored to the shore. It never moves. And what happens is the river is flowing to the left. And so what happens is you have a basket here and a paddle. And then there's an opposing basket and an opposing paddle. And then there's a chute right behind my hip there. You'll see a flat chute on that basket, and there's another chute. These baskets have a chute. And then there's this box on the side. So what happens is, just by the current of the water, it catches the scooper, you know, the wire basket, and it pushes it, and you get the paddle. But if the salmon are just swimming up, they just blindly swim into the basket. And then the basket goes up, the salmon falls onto the chute and shoots right into the box. It's the most ingenious thing, and it works great. And then the next basket comes around, and so on. So after a few hours, when the salmon are running, that box is full of fresh salmon. It's incredible. So that's a fish wheel. And there I am holding a salmon. So because we hire local people who live there to be our maintenance staff at the site, they have access to this. So they would go down and get us salmon, and within an hour or two of being caught, they're on the grill and we're eating them, and it is so delicious. So that's a fish wheel, but you see them all over Alaska. If you're a tourist, you got to buy salmon roe, eggs, put them in a little sack, put a weight on it, get a pole, throw it out in the water, and spend hours and hours dragging that little sack of roe. And the salmon want to put the roe in their mouth and move it somewhere to fertilize it. So when you feel them moving it with their mouth, that's when you set the hook. But this is way more efficient. The Alaska pipeline is also very close to the HAARP site, 15 miles away. This is a 4-inch diameter pipe with an insulated coating. Notice the bumpers here because of the expansion and contraction, largely due to temperature changes. In this interior part of Alaska, it is not unusual to have 40 and 50 below Fahrenheit, minus 40, minus 50, and it gets as cold as minus 60. Now, I've only experienced minus 52. But, and then in the summertime, it'll go up to like plus 90 occasionally, but it gets brutally cold for many, many months. So the pipeline is on a sled here and has bumpers. Notice the thermosiphon technology in play here. See their thermosiphon, same technology we're using. Okay, here's, we're gonna wrap this up. Here's a picture of the HAARP site with what's called hoarfrost. And I'm standing in the operations center building. And looking, you can see this the size of the HAARP array here. And it's just huge. So here's just the HAARP array at minus 40. We can operate at those cold temperatures, no problem. The frost doesn't bother us. Here's a view of the HAARP array. Look at the ground screen. There's our ground screen right there, that 18-inch square, that AlumaWeld ground screen, 15 feet up. You can see sort of the cage dipoles for the low band, matching units, the high band. There's a truck back there. Somebody's working in a shelter building. And here's our, we have 30 shelter buildings with 6 transmitters per building and the control rack. Everything is done over a LAN. So the last few comments here are that the HAARP transmitters for the broadcasters, which we all are, I guess, in the room, the efficiency of a HAARP transmitter is 42%. Not going to sell one of those. But that's because they're all linear amplifiers. The whole chain, the push-pull 10,000, it's all a linear amplifier system for signal purity, low phase noise. So that means our prime power, 480 volts AC, 3-phase, a properly tuned transmitter is pulling 62 amps per phase for 3 phases for one transmitter. Or there's 2 10 kilowatt amps to be putting out 10 kilowatts, 20 total. So it's a 600 amp per phase panel in each building. We send 12.5 kV up the road, and then we have 2 pad mount transformers, well, 1 pad mount for 2 buildings, and so we can't take 480 too far. The other thing I want to comment on, which somebody will probably ask this question, so I'm going to head it off, is remember I said we're using 1 5/8 solid foam dielectric coax, and it comes out the side of the transmitter shelter buildings here. One is their east-west output, north-south, up to its tower it's permanently married to. So the way we ignore these coax lines is every single coax line for every transmitter is connected to towers on either side of its own shelter building. So the coax lengths can all essentially be the same. So we have them built to the same electrical length. So the phase delay is the same for all transmitters. That way, they all move at the same time in the same way, and we can completely ignore them because they're all moving the same way at the same time. So that's a constant that we can now ignore. So anyway, there's a lot going on at the site, but that's just a quick view, and that's all I have time for tonight. So if anybody has any questions, I'm happy to answer them. There is a ham call sign, as I told many people in the room, for the site, kilowatt Lima 7 effective radiated power, as I mentioned earlier. So if you hear somebody using that call them, because they're sitting there at the site. And one last comment, the site is oftentimes remotely operated now. We like to operate the site and run experiments being there because we have real-time capability to diagnose and make things happen. And most importantly, when scientists show up to run an experiment, Dr. Hutzefritz shows up and he's going to do some crazy thing, and he's got to put some receivers out there, and he opens up a box and all this Radio Shack parts come spilling out and alligator clip leads and everything else. We're like, that's not going to last in the snow. It's 30 below out there. So we have to help re-engineer a lot of stuff and help them do their experiment. So it's better to be there. But today, the site is often operated remotely, and our chief scientist, Dr. McCarrick, is in Oakton, Virginia. And he's oftentimes operating the site remotely through a secure internet connection to Oakton, Virginia. Not always, but often. Okay, questions?
You mentioned the backscatter radar in Ukraine. Is that the woodpecker you're talking about?
No, Sura was an ionospheric excitation research site in similar vein of HAARP that was built during the Soviet Union in the Ukraine. I don't know the status of it now with the war. I have no idea. It's probably damaged or maybe just destroyed. But of course, the Russian woodpecker was an over-the-horizon backscatter radar that was in northern Ukraine with a separate transmitting and receiving sites called the Duga radar, but that's a separate system.
Trying to make sure that everybody can hear the question, but
I can move this around.
what's your relationship with lightning?
Well, nobody has a good relationship with lightning, right? The good news in Alaska is they don't get a lot of lightning. If Florida is the lightning capital of the world, so I'm told, Alaska is probably, you know, the minima in where you're going to get lightning. So there isn't much lightning up there, but there is lightning occasionally. The site has never been hit to my knowledge, but in each antenna matching unit at each half dipole, we have a ball gap that will flash at a certain voltage, and all of our 28 volt DC control lines for those vacuum relays to release half dipoles and run the high band low band switch. Those have, you know, real professional quality surge protection on them. But lightning is a rarity in Alaska, thankfully. So I guess I would say my relationship up there is good.
I know I meant. Well,
People,
oh, the Zoom.
yeah, Zoom
Okay.
so they can hear.
Sorry. So you mentioned the drivers, a little bit for the grounded grid amplifiers, but you're probably gonna need pretty hefty drivers if they're grounded grid. What do you really have for the drivers? Do you have like IQ where you can do just arbitrary anything, or is it like you have a fixed AM circuit and a fixed FM and you can just switch them in and out?
Okay, that's an excellent question. I'm going to answer it really quickly in two parts. From an RF power point of view, which I'm not sure you're asking that part of it, but from an RF power point of view, you know, we have two solid state broadband amps nominally running at 20 watt, but we come in at plus 10 dBm from our RF source, which I'm going to talk about in a second. Then we go to roughly plus, it's a 50 watt amp that nominally runs around 20 watts. That then drives a single broadband MOSFET amp, because that was the technology of the day. It's a bunch of MRF 150s, which everybody knows. And that's a 1 kilowatt amp that nominally broadband runs at 500 watts, and that drives the push-pull pair of 4CX 10,000Ds. And that amplifier stage of the 10,000Ds has 13 dB of gain, obviously. So we do obviously get gain out of the grounded grid amps. But in terms of modulation source and the actual exciter, and I'm happy you asked that question, because you know, we took a unique approach that we may not have taken today with all the DSP. But basically the answer is very simple. We have two extremely low noise Agilent signal generators that sit in a shelter building in the center of the array. And that's our SIG-Gen 1, SIG-Gen 2. And then we have two parallel RF distribution networks with line amps, basically, low phase noise line amps, that then branch out from going across a row up the column. And basically each shelter building has two inputs of 3/8 inch Andrew Heliacs. Here's SIG-Gen 1 and here's SIG-Gen 2 at the right level. And so those are our carriers. And they're just an amplified distribution chain from two signal generators. And those signal generators do FM and phase mod. But then in the transmitter, we can do AM pulsing with user-defined rise and fall times to limit our occupied bandwidth. And we can do single sideband and all those different things that are amplitude. So amplitude's done in the transmitter, the carrier and the FM and phase mod come from those master signal generators that come out of an RF distribution network to each building. Does that answer your?
Yeah, are you doing like class E or something, FETs in the, like you're doing modulation of the transmitter stages themselves for that?
No, we do all of our modulation down at the plus 10 dBm level
Okay.
and then just linear amplify them.
Is that where you do phase too?
Well, the phase is done on the carriers. Phase and FM is sitting on the carriers, which is done in the signal generators, and that just passed through this row column RF distribution chain. So the interesting thing about the RF distribution chain coming out of those generators is we want that RF to arrive in every shelter building at the same delay. So shelter buildings that are close to the signal generators, there's a box underneath the shelter building, a wooden box, and there's all this coax coiled up like crazy because they're trying to get the same delay that the transmitter buildings on the far edge have virtually no coax coiled up. But this is the advantage of operating at 10 megahertz and down. The losses in the coax, even 3/8 inch, is not very high. But I want to tell you one funny joke real fast on that. Every time I would go to Agilent Technologies and do things to build this site, and I would get the applications guys on the phone, and they would say, what frequency are you operating at? And I would say 2.6 to 10 megahertz. It would take me 10 minutes to convince them it wasn't a clock. They couldn't believe I was actually having an RF carrier at that low frequency. They're not hams, obviously. So that was always a strange hurdle.
For Zoom, we just have a comment from Tim Sawyer. There was a fabulous presentation. Thank you. And Robin Williams. Very nice presentation. NASA Alaska Satellite Facility from UAF Fairbanks is not that far away. Had to tell them about it. So I don't know what that is, but maybe you do.
Well, thank you for the nice comments. I don't know that facility, but I'm talking to the people at the University of Alaska Fairbanks all the time. So I will talk to them about that and make sure that they make contact. I'm sure they're aware of it. Alaska is a big place, but it's one small town.
Are you gonna come up? Okay.
Well, actually, I can answer your question. So the, up in Alaska, Fairbanks also runs NASA tracking stations up in Alaska. So that's just south of Fairbanks. So they brought a bunch of antennas for NASA there. So that's where I think that's one of the guys that actually works in that facility out there. Yep.
Okay, well, if they work there, I encourage them to call the UAF Geophysical Institute and ask for the HAARP program office and introduce themselves. By the way, since we have a lot of engineers in the room, here's a funny factoid for you. So we all know that HAARP is transmitting generally vertically, so we're getting an NVIS bounce, right? So one of our diagnostic receivers in the Anchorage area, but just a broadband, kind of broadband dipole, it's an OCF dipole, and a flex radio is the receiver. We remotely use it as one of our diagnostics on a rooftop in Anchorage, Alaska. We typically see an NVIS signal level from our site 200 miles away at plus 10 dBm. And flex radio is pretty accurate at measuring received power, and it'll move from 0 to plus 10 dBm. And then that's the NVIS bounce coming from 200 miles away. Amazing. So the site is very active. If anyone in Goddard or anybody wants to get time on the site, it's readily available. There is a pay-to-play kind of strategy here, but the site is running beautifully. In fact, the site is operating right now. There's a summer school called PARS, and it's Polar Aronomy and Radio Science. And students, graduate students, are up there running experiments. And I want to comment briefly about running experiments. A site like this, we run on a campaign basis. So that means experiments will be proposed, accepted, and they'll be given a time slot say, in March, for like the last 2 weeks in March, the site will come up and operate, and we might have 8 or 10 different experimenters doing completely different things. So the way HAARP works fundamentally is that the experiments will be dry run on a simulator, a software simulator back here. So we know how we want to configure things, or whatever crazy waveforms and beam angles and everything that they want. Then what we'll do is we'll go up to the site, we'll pre-tune and get tunes, because each transmitter has to tune its output antenna tuner. And so we'll pre-tune everything and dry run everything in all of our different bands. And then the GUI software will automatically execute these experiments in a time interleaved fashion. For example, let's say, for example, we've got, let's say we have 6 experimenters. For the first 10 minutes, experimenter 1 might be doing over the horizon radar work. Then the GUI software will automatically drop off. It'll completely change itself to experimenter number 2, who might be doing optics, and he'll get 10 minutes. And then the next 10 minutes will drop off the air. Everything will go to a whole new preset and tune, and then they'll be doing, deep space radar work. And so we just keep interleaving. Every hour we keep interleaving at some time spacing all these different unrelated experiments, so everybody gets time. And then the ionosphere is changing, right? So then if the muff moves lower, we just move to our next lower band and keep that cycle of interleave experiments going all night long. So everybody gets a chance.
Do you do anything special for peaks and when the solar cycle is really going, it's about to or is now?
You mean the solar cycle peak? So his question was, do we do anything special when the solar cycle is peaking, like it's ramping up to a peak now? And that's an excellent question. So for those that are not familiar, the sun has a solar cycle that's an 11-year sunspot cycle, as they call it. And as the sunspots rise up in frequency, that means the ultraviolet radiation basically is coming to a peak. And that excites the electrons in the ionosphere, and the maximum usable frequencies move much higher for both the oblique long range and the vertical incidence. They go much higher, and the efficiency of those refractions goes up. And it's great fun. And the peak is 2025, I think it's the peak this year. So we're ramping up. So generally the solar cycle peak doesn't have a big impact on what we're doing, except, and there's a funny story behind this. When we finished the site in 2007, we were going through acceptance testing, and everybody was all excited to get in and do their science. We were pretty much right at a solar peak. And the MUF had moved up to about 11 to 11.5 megahertz because of the solar cycle peak. Well, that's a problem because we can only transmit up to about 9.995, not on top of WWB at 10. But the problem is we were too far away from being just below the MUF, where we're most efficient. So we're like, darn, we just finished it. And now the MUF is going a little bit too high for a while. So the solar cycle peak is probably hurts us a little bit more than helps, except at night, it's not falling below 2.6. So that's the helping part.
Let's invite anybody on Zoom.
Yeah, does anybody else on Zoom have any questions, Eric?
There are no new ones except
Go ahead and invite.
the one question that we handled earlier. They said the big dish is at the LV building.
Right, that's one.
So that's more that NASA Alaska satellite facility. If anybody in Zoom wants to ask a question, not in the chat, just go off mute. We'll hear you. Otherwise, we've handled the questions in the room here.
I must have put everybody to sleep.
They're pretty much all there.
Here, Fred, did you want to?
Yeah, sure.
Talk about your RF safety provisions. Can somebody be out under those antennas if you're transmitting?
Yeah, I'm wondering about the hotspots. They must be very hot.
Okay, that's a great question. I can certainly answer that for you. So obviously, with 180 transmitters, 20 kilowatts each transmitter. So that's 3.6 megawatts of RF input power into the array. That's a lot of power. So the first question was RF exposure. Well, of course, the government was very concerned about that. So they had a team of PhDs who were expert at measuring RF exposure. And they came up and spent quite a bit of time and had us operating all kinds of crazy parameters and pointing angles and frequencies and every variable you can imagine. And they measured the radiation under the screen, and they measured the electric field strength, outside of our fence. And they came up with an interesting result. And the result was that outside of our fence, which just sits just a short ways outside of our ground screen, the electric field strength from the AM station, KCAM in Glen Allen, 5 kilowatt carrier power, 20 miles away, was stronger than our own signal. And at first I thought there's something wrong here, but it turns out the beam forming is so strong. It's so strong with an array this big that our energy down as those ground level angles off the ground screen is exceptionally low or extremely safe. Now, when you get under the ground screen, it's extremely safe, except the guide strategy in the array is we use Philly strand coming down through the array, which is non-conductive, of course, but once it comes through the ground screen, then it converts to a steel wire to go down to the piling of an adjacent thermopile to anchor to. So there were cases where that metal had poked up a little bit above the ground screen, and there was a lot of RF energy on those metal ends for the tower guys. But that was the only danger area where you could get burned. And so we just stayed away from that, and we established a policy of not going out under I used to go out there and just wander around and just look at transmitters. But then I thought, why should I? I don't need to be out here, and it's kind of silly, but it's very safe under the ground screen.
I would imagine the size of the human body, you're not talking any kind of resonance at with that kind of wavelength, you're just right on
Let me share one more funny story with you, because Alaska is such a funny place. So when we built this array, you can see that we have these cage dipoles where they go out to the side and come down and make a box and all. There's a lot of wires, there's a lot of interconnections, and everything is supposed to be welded to plates where the wires of the cage dipoles come together and at the feed point and so on. So obviously contractors are not perfect. It's not a perfect world. And so we noticed when we first brought the array up that on our aircraft radio at 123 megahertz, we're getting a lot of noise when we're transmitting. And I thought, uh-oh, we got arcing out there. So everybody's like, oh no, how do we find it? And so I came up with a clever plan. And this is why being a ham really pays off. Because I said, okay, when it gets dark, really dark, we are going to put a 1 kilohertz, 100% AM square wave on all the transmitters. And we went out there in the middle, underneath the ground screen when it's transmitting away, it's safe, and we could hear a 1 kilohertz tone. And so one by one, we turned transmitters on and off, and then it led us to a tower. And then sometimes we could see the little blue flame. So we debugged our missing welds using a 1 kilohertz, 100% AM square wave when, at night to see the little arcing and to listen with our ears. And that just worked great. So one of the experiments, by the way, it's very active now, is over the horizon backscatter radar experimentation. And the reason is twofold. One is that the northern passage above Alaska is thawing rapidly. There's a lot of shipping traffic, a lot of military activity, and they want to have surveillance of this. But the problem is HF propagation in the auroral zone is very difficult to model. But they want to have OTH backscatter radars as opposed to microwave, which you have too many sites and to be too expensive line of sight. So we're really characterizing the ionosphere and really pioneering the application of over the horizon backscatter radar in this region. It's really exciting.